It's my pleasure to introduce Dr. George Xu today. He has the LSU Coupled Ocean Modeling Group, one of the largest regional modeling group in the Gulf of Mexico, and then the top supercomputer user in the state of Louisiana. His group used state-of-art numerical technique to represent the interaction between land and ocean processes along the Gulf Coast. Every year, his group consumes more than 10 million service units to simulate, assess a wide range of coastal hazard, including hurricane, compound flooding, land loss, eutrophication, hypoxia, ocean acidification, and others. Since joining LSU in 2014, he has raised more than $44 million in external funding for LSU as a PI or co-PI from various federal and state agencies. He received the 2020 LSU Rainmaker Award in the mid-career categories of science, technology, engineering, or mathematics. So only one LSU faculty member campus-wide receives this distinguished honor each year. So please welcome Dr. Su today. Whenever ready, you can start.
Thank you. That's a very nice introduction. And by the way, I got the award, but one of the letter writer I know is from UT Austin. So thank you all. Yeah, and welcome to SEC. I'm George, and I want to start my presentation today with this animation. If you scan here, or I have the sticker in the back, if you scan here, it will bring you this operational website we are building now. So far we have Mississippi River model and ocean circulation online already, and but very soon, I think within a month, we will have the compound flood model for the Houston area, hypoxia, and the NPZD carbon model be online as well. So this is the operational modeling system we are building as of now. And the topic of my presentation today is how to use a regional Earth model system for coastal hazard forecast and handcast to understand what's going on. When I was first hired at LSU back 10 years ago, this is my 10th year at LSU, the position called coastal hazard is never physical oceanography, geological oceanography, or like chemical oceanography. It's called coastal hazard. And at that time, I was a modeler, work on the Gulf, but located in North Carolina. I have no idea about how many coastal hazard we have in this area. But 10 years later, so guess what? Yeah. So I will show this. So coastal hazard, we live in the Gulf, like we share the Gulf. We know there's many types of hazard. And we have long-term and we have short-term. So for example, like warming, sea level rise, everybody knows that. But something new this year is temperature. So we know that last summer was very hot, and it will kill the corals in the Florida, and there are some new troubles we see. So for example, this is the saltwater intrusion in New Orleans. And Army Corps of Engineers, they have to put a barrier somewhere near New Orleans to stop the penetration of salty water. That is because last year was very dry. And also because of the drought, guess what? We began to have marsh wildfires in Louisiana. Can guess that, right? So this is just a photo shows south of New Orleans. So they have this like marsh fire last until I think late October. So in addition to this new, I think that we call it cascade hazard from global warming, climate change. We also have like hurricanes, right? And land loss. So this is a mangrove. This is a newly emerged mangrove shrubs in the Barataria Bay, somewhere south of New Orleans. But you can see, I don't think they're gonna last for a long time because of the land loss. And look into the future, we can expect a weaker Gulf Stream. So we have long-term, short-term, all kinds of like coastal or ocean hazard. In the background, you'll know that this is primary productivity, which the elevated primary productivity from the Mississippi River many times will give us trouble of hypoxia. So what is a regional Earth system model? This is from ChatGPT, right? So a regional Earth system model is a specialized type of computer model designed to simulate and study the Earth's physical, chemical, biological process at a regional scale. And specifically, it have a spatial focus. For example, the Gulf, that's a regional. And usually it should have a higher spatial resolution compared with a global model. And it can have like atmospheric component, ocean component, land surface component, and also within that, there should be some biogeochemical cycles. And we can use data simulation and different customization to increase the representation of the dynamics on the local scale. So this is what I get from ChatGPT, very powerful. So my talk today will center on this coupled modeling framework we call a COAWST. COAWST is short for coupled ocean, atmosphere, wave, and sediment transport modeling system. It features atmospheric model, WRF. Wave model can be either SWAN or WAVEWATCH III. Ocean model is ROMS, and within ROMS, we have very mature biogeochemical cycle, sediment transport module. And a new module my group introduced to this platform is land surface / hydrological model. And we have been keep developing a LSU version of WRF-Hydro. And we were able to coupling WRF-Hydro with ROMS model. So most of my talk will be centered on this kind of complicated modeling system. So this is some examples about in-house model development. We not only use model because all the models I mentioned here in this slide is open source. So we can develop this model. So we have our own in-house, for example, we have a fluid mud module. We have sediment-induced light attenuation module. We introduced a sediment model into WRF-Hydro. And we have our own in-house oxygen model that is for hypoxia. Carbon cycle, and the last one is this, we call it dynamically coupled ocean river modeling system. So we are not only model user, we also do tons of model development. You can hear me well in the back or? This is kind of my outline of today's talk. So I was by training a sedimentologist. My PhD was about the Mekong River Delta evolution during the late Holocene. So although now I'm a modeler, but I still have this very strong sense of temporal. So we need to understand the temporal, how these things evoluted through this timeline. I will start with some compound flooding simulation that will be for Harvey and Florence. And then I will talk a little bit about the shelf sediment and biogeochemical dynamics. This is simulations mainly circular around Gustav back in 2008. And then some carbon dynamics in the shelf that is around Laura, that is 2020. If time permits, I will also present some new result based on machine learning and artificial intelligence. That application is for a hypoxia. So the idea here is we have some short-term disturbance, right? But our model is we runs all the way from 2000 to 2020. So we have 20 years model handcast, can largely fill the gaps in in situ observations, and build on that 20-year handcast. We can train a machine learning / artificial intelligence model to work on different topics. So this is overall outline here. Perfect storms, compound flooding, Harvey. You all in Texas, you all know better than me about Harvey. So here we want to address is, I want to address is the compound flooding part. So you can see there are some scientists, although they might not associate with academia environment, but you can see that is prior to Harvey's landfall back in 2017. And this guy already point out that there will be a compound flood in this area, and he called this a battle zone. I think the battle zone is very good. So this is gonna be the battle between the fluvial flood against surge, right? So this is the compound zone. So this is some details about what is a compound flood. So for example, this is a result at these buoy locations, and this is a paper from colleague from Florida. So we can see that the evolution of Harvey is from here all the way to Manchester, Bayou Manchester, right? So you can see here on the ocean side, we see this surge signal, right? But as we move from the ocean side toward the land side, hydrology side, we began to see a huge amount of water actually will get into the Galveston Bay after the landfall. So this is surge, that is rainfall. So this is compound flood. So to study compound flood, there are some papers, one from went home, this is on the right-hand side, but the first paper, modeling paper, I think is back in 2020. And in that setup, use ocean model and prescribes like the point source, river source along at the 3 point you can see there, right? And use this kind of a setup, like they can also isolate, they try to isolate the impact from river and surge. So for example, like in the model setup, they can enable or disable the point source, right? So, but in this case, they only use two rivers. So you can see that one is Buffalo Bayou, the other is San Jacinto River, right? So these two rivers. And in Van Hoon's paper is much more advanced setup. So you can see the coverage is much better and features a high resolution. The modeling grid is built all the way in the Houston area, right? And also utilize the point source from USGS river gauges. And we can also diagnose the impact from wind, plus rain, and the impact from wind plus rivers, and all combined. So this is, we can use numerical model to isolate the different contribution from different processes. So the method or the technology my group is using is slightly different from this effort. So what we do is that we couple the hydrology model. So we use a model output to hydrological model output to drive the ocean model. So on the ocean side, we have COAWST, right? So COAWST, at that time when we first published that paper, COAWST does not include hydro model. So what we do is we couple the ocean model on this platform with the WRF-Hydro model. And the WRF-Hydro model has 3 different components, has subsurface routing, channel routing, overland routing, and the precipitation and atmospheric forcing was provided by NOAA-MP, which is also a UT product. So in addition to the public released WRF-Hydro, our group, we modify a lot of algorithm in WRF-Hydro to make it more suitable for compound flooding simulation. So for example, we created this kind of we call a diagonal flow algorithm. And also we introduced the local inertial term into WRF-Hydro. So by default, if we activate channel routing in WRF-Hydro, the water can only get into the channel. They can never overbank flood, get back to the land. But we disable the channel routing. Instead, we treat the hydrology model as a shallow water model. And in that case, the water can flow freely, get into the channel, and then overbank flow. And the other technology is we use this coupling method, which means that this is these two models, the ocean model and the hydrology model, they share the exactly same computational grid. But for ocean model, this is land mask. For hydrology model, this is ocean mask. We artificially fix this fixed boundary along the 0-meter isobath. So this water, sediment, salt information will be exchanged dynamically between these two models every 3 seconds. So we run these two models simultaneously, right? And every 3 seconds, these two models talk to each other along this preset boundary. So this is we call dynamically coupled modeling system. So some demonstration. So for example, like this is a handcast for Hurricane Harvey. This is our model domain. So again, so this is hydrology model, and I'm sorry, this is hydrology model, ocean model, and ocean model hydrology model. So we can compare the setup of 3 different experiments. So on the left, that is ocean model only. And in that case, we turned on the wet and dry, so which means that the water can't get into the land part from the ocean model. And at the second, the one in the center is we use output from National Water Model, which was built on WRF-Hydro at these 3 points, and we inject the output from National Water Model as a boundary condition to drive the ocean model. It's think about you send out a telegram, right? So it's like the river model send a signal to the ocean, but you never know if they got it or if there is any feedback. And the last setup is modern technology. It's like 2 people talk to each other, right? So we have ocean model fully coupled with the hydrology model. This is why this animation stopped, right? And you can see this is a model coverage of the hurricane event. This is a Galveston Bay, and you can hardly tell there is a boundary, but the boundary is somewhere here. So on their part, WRF-Hydro handling all the flooding, and in this part, that's the ocean part. So this is different in terms of spatial coverage. And improvement also at this, we look at a different gauge station, including the USGS gauge. But here I want to show the gauge in the bay. So 1, 2, 3, 1, 2, 3. So you can see that the black line here, that is observation. Red line is fully coupled model. Blue line is ocean model when we driven by the National Water Model. And the last one is ROMS model. So you can see the improvement is significant. And now we can achieve the R² all the way to almost 0.9. So that is the improvement compares against when we link the model and ocean model only. So Florence, the model was built on the Florence. So that is when I first got the grant from USGS, we worked with John Warner at USGS. The first hurricane indeed we worked on was Florence. And then we moved to Harvey, right? But I know Florence happens later than Harvey, but in the year of 2019, we began this work. We tried to work on Florence. The comparison between Florence and Harvey, you can see that this is the geographically of the bay is different. So for Harvey, this is kind of like a lagoon or a bay system. We have this barrier island, right? But for Florence, this is Cape Fear. This is the Cape Fear estuary. So you can see that it's kind of like shotgun style estuary. And when we set up the model, and so this is location of some USGS gauge. Together, this is some points where we have this, we call the high water mark, right? So that is the USGS gauges. So you can see the correlation is very good. And I want to have your attention here. So you can see this is a computational domain. Again, WRF-Hydro, ROMS, right? And for ROMS, that is a land mask. And for WRF-Hydro, this is ocean mask. The computation is not that expensive. So for example, this domain features about 100-meter horizontal resolution. And we use 400 cores. And for a 72-hour forecast, it only takes about 1 hour. Yeah, so this is computationally is affordable. And some difference. One location here, this is a no-wide tide gauge. That's the second one. So you can see here along the coastline facing the open ocean, all setup performed similar. Right? So we have observation again in black line, ocean model only. When we drive ocean model, fully coupled ocean two-way model, they all perform similarly. So the difference is in the estuary right here. So you can see here, if we use an ocean model only, it will largely underestimate the water level. But if we use the output from National Water Model from Tuscaloosa, it will overestimate the water level. And use our coupled model, you can see these two lines match very well at least in this area, post the landfall of a Hurricane Florence. This is where the pluvial flood dominate this area. And we can also zoom in and look into the estuary water level. So this is, again, we have one-way coupled model. These two are more or less similar. We are testing different physical algorithms here, but you can see here, this is along the channel from 0 to 100 to 50 kilometer. So you can see among the different experiments, the difference in water level simulated throughout the hurricane. And specifically, you can see coupled model is blue or red, but the one-way linked model will largely overestimate upon the end of the simulation. We'll begin to see the water level simulated by the national water model driven ocean model will be largely elevated compared with our fully coupled model. Here we go. This is post the landfall, and we can see the difference. So this is the development of water levels in the estuary. And so the idea we proposed in a new paper that is under review is the compound flood compared with a nonlinear flood. So we talk about compound effect compared with a nonlinear effect. So we talk about like compound flooding, but what is compound flooding, right? So it's 1 + 1 bigger than 1. So we have a surge happens at the same time we have river flood. So these two effects combined together will be definitely bigger than only one effect. So that is 1 + 1, definitely bigger than 1. But the nonlinear effect here is that if 1 + 1 = 2, right? So many times we tend to use we call it superposition, right? So what is the maximum like surge introduced by what is the maximum like water level induced by surge plus the water level induced by flood? But what we found is this distribution specifically for the nonlinear effect is not uniform everywhere. So at a certain location, we can find the nonlinear effect. Here, if we see a red color means 1 + 1 bigger than 2. If you see a blue color means 1 + 1 smaller than 2. So we can see here at the head of the estuary, this where we can find most of the nonlinear effect. And the compound effect is throughout the river and the coastal system, right? So we can achieve this by carry out a series of sensitivity tests. So for example, in this case, we have 6 experiments. We have a ocean only. We have a like fully coupled model, which is experiment 3. Then we can disable the precipitation. We can disable the wind, just like the paper, the method used in Van Hoon's paper. And then we can diagnostic the impact by examine the difference among these different experiments. So it shows like, you can see this is a nonlinear effect. I know it's not, but on my screen, like the red color is more vivid. It's mainly in this area, and the blue color is in this area. So one quick slide is that we are also trying to couple like salinity between these two models. In the background, that is a Landsat satellite. I think that is the most famous, like the signature like satellite image for Hurricane Florence. So you can see that this is sea-down. You can see from the creeks, right? So this is the sea-down. We know that North Carolina is very famous for hog farms, right? So there's a lot of like hog lagoon. So this waste was washed out and get into the ocean. That's where this color comes from. And again, if we use a linked ROMs, this is salinity. So we are using salinity as a representation of pollutant or the particles in the ocean, right? So this is, we use a one-way driven model. And you can see the difference in dynamics. This is a fully coupled model. So this we can show the salinity. And specifically, for example, here on the land part, this is, the salinity here is handled by WRF-Hydro, by the river model. So the ocean will just transmit the sea level, water and sediment signal to the hydrology model. And then we can see there's some salty water here. The idea is we try to understand the ponding time. And we know like after each hurricane, there might be some salt water pounded in the marsh, right? And the freshwater marsh, they don't like that. Yeah, they might kill the freshwater marsh. So this is, we are writing another paper, try to understand the pounding time introduced by a storm or like a tropical cyclone event. So this is, for example, this is, you can see the salt. This, any color is salt, right? So this is the evolution of the salinity during a hurricane event. So far we talked about compound flooding, right? So we focused on the two-way coupled model, and in the next few slides, it's gonna be shelf dynamics in terms of like sediment, biogeochemistry, and carbon dynamics. So let's look at into the offshore. So this is a handcast for Hurricane Gustav back in 2008. On the left, this is the sea level pressure track line. And this is a vertical profile along the 50-meter isobase right here. So we stretch it, right? But you can see like temperature, salinity. So this is Mississippi River going this direction, right? And this suspended sediment. So you can see that upon the landing of hurricane, we can see there's a boom, like the sediment are resuspended and get into the water column. So then we are not satisfied only looking into sediment. Sediment is of course very important, but how about the turbidity introduced by sediment, right? Will that affect the primary productivity in the on the shelf? So in this case, to study this Hurricane Gustav, we have to run a like 20-year handcast, so we can extract the model output as initial condition. So we have this fully coupled physical-biogeochemical model running for 20 years. And then we extract the snapshot upon the landing of Hurricane Gustav. And here we run the fully coupled ocean atmosphere wave sediment plus a biology model. So what we learned from here is, so again, this is a track line of Hurricane Gustav. And if we look at this transact right here, you can see from 0 meter to 50 meter. This is suspended sediment concentration. You can see here comes the hurricanes, suspended sediment transfer, right? And on the top, there's two experiments. The top is if we don't consider any shedding effect from the turbidity, what is the primary productivity looks like. In the middle, this if we introduce sediment-induced attenuation to the biogeochemical model in the ocean, what is the primary productivity looks like. So you can see there's a difference. And if we look at the satellite image, it will be a better storyteller. So sea waves prior Gustav, and that is post-Gustav. And we want to focus in this area. So you can see that there is an offshore bloom after the landfall of Hurricane Gustav. And on the bottom, that is a model simulation. One is if we consider the shedding effect of sediment. One is if we don't consider the shedding effect from the sediment. The story or the science we want to tell here is that whenever the hurricane make landfall, a huge amount of sediment will be resuspended, get into the water, and they will provide a shedding effect. So a huge amount of nutrient, mainly delivered by the Mississippi River, they cannot be used because there's no light, right? So they will be somehow preserved in the shallow water. And then when the condition is right, they will be export laterally, go to the deep water, the edge of the shelf. So that explains this post-hurricane like algae bloom. So this is how we try to couple like ocean model with biogeochemical model and sediment model, try to understand this like primary productivity disturbed by a hurricane event. Carbon, this is a hot topic now, right? So first of all, I want to give everybody a quiz. So this is 2020 hurricane season, 20 hurricanes or storms in the Gulf area. We have a one buoy located right here. This is called coastal LA. And this buoy is equipped with carbon sensors. So this is a carbon dioxide concentration. We talk about sea surface carbon dioxide. This is air, right? Air is kind of like flat, always around 400. This is ocean surface. And in other words is that if ocean is lower than air, we know ocean serve as a carbon sink, right? And vice versa, if the value is bigger than the atmospheric partial pressure, then ocean began to serve as a source. So what happened is right here, upon the landing of Hurricane Laura, we see this penetration of sea surface carbon dioxide concentration. So the ocean shift from a carbon sink to a carbon source, right? And the quiz here is what caused this? And this is also the hypothesis we proposed to a NSF rapid project is A is carbon released from the eroded soil. There's a lot of carbon, right? And in the soil, there's a lot of like erosion. So once this dirt being transported to the ocean, the carbon will be released back. So the ocean become oversaturated. So introduce this like shock. The second is upwelling of carbon dioxide reach deep water. Makes sense, right? Hurricanes is upwelling system, and the water, the deep water has more carbon. So there should be more carbon being transported to the surface ocean. C is the changes in Mississippi River plume dynamics, right? So the Mississippi River is right here and not far away from this buoy location. Mississippi River delivers huge amount of nutrients and also carbon. So that's the C. And the last is the resupply of oxygen. We have a lot of oxygen being pumped into the water column because of the strong like turbulence introduced by the hurricane. So it will resupply oxygen and they will increase the respiration of organic matters to release carbon to the ocean. All four make sense, right? And I think by the time we propose to NSF, I choose A, carbon released from the soil. Why? Because I jump a little bit here. Sorry, because if we look at the Barataria Bay, again, this is the Mississippi River, and this is the Barataria Bay. We have two experiments. This is carbon. So if there is no erosion, means no carbon released from the soil, what is the sea surface carbon dioxide looks like? And this one is if we consider the carbon dioxide released from the soil, what the sea surface carbon dioxide looks like, right? So, and for information, the buoy is right here, somewhere here, okay? So you can see that if we consider the erosion from the land, we'll see a supersaturated surface water, right? So in that case, like the small bay no longer serve as a carbon sink. Instead, it will release carbon back to the air. So this model we build is very, I will not go to the details, but like we consider all the biogeochemical processes. We have different like phytoplankton groups. We have inorganic carbon, organic carbon. This is the flow chart. And we also consider air-sea carbon dioxide exchange. So to achieve any model, so again, the first thing is we need to run a handcast. This is what we learned, cover the entire Gulf of Mexico, right? So we have this regional model. We run the handcast for 20 years, and this is the condition over the past 20 years in the Gulf. So from top to bottom, we have red color standing for the open Gulf of Mexico. The blue color stands for the northern Gulf of Mexico. So you can see that the two waters show a similar trend. Carbon dioxide, sea surface carbon dioxide increasing, pH value decreasing, saturation rate decreasing. All right, so this is the ocean is getting more and more acidic. So we can do a lot of analysis on this kind of handcast. So for example, at that same buoy, remember that buoy, right? So this is where we gain our confidence. So this is a model data comparison at that buoy for sea surface temperature, sea surface salinity. And this is the carbon dioxide on the sea surface. So you can see the blue color is model output, right? And the reddish color dot, this is a buoy record. So you can see that we can capture this carbon dioxide dynamics in this location very well. And if we look back what happened over the past 20 years, you can see that, again, this is the coastal LA, Louisiana buoy. Another buoy located in Mississippi in the state of Mississippi coastal water. And we compare our model output, which is in black line, compare with the buoy, right? This is climatology, buoy, and against all the different global models or other published regional models. So that's where we gain the confidence in our model performance. Yeah, so I didn't show much like validation for other models, but I think for carbon, which is very tricky to simulate, but we have very good model performance. And I will skip this slide. With this 20-year simulation, we can look, of course, hurricane events, but also we can look into like different climate. For example, the year of 2019, there's a big flood year, right? And compare with a dry year, 2022. And we never imagined that 2023 is even drier, right? But this is dynamics in the shelf water. You can see a flood year. This is carbon dioxide, sea surface carbon dioxide concentration. This is a dry year. So this is a comparison in spring, summer, and compare with spring and summer. So what we learn from here is that if we have a dry year, right, the overall primary productivity will be reduced. So the ocean will serve as a smaller sink for carbon dioxide because we know that the nutrient delivered by the Mississippi River will stimulate the primary productivity, so the ocean can continuously serve as a carbon sink. But in this deltic area, right off the Mississippi River, right, the more river water is, the higher concentration of carbon we can expect. In other words, is that in this case, the Mississippi River acts like a double blade sword. So on one hand, the nutrient delivered by the Mississippi River, they will stimulate the primary productivity, will draw down the carbon dioxide, right? But on the other hand, if the Mississippi River itself delivers too much carbon, it will make the seawater, at least around the deltic area, oversaturated with carbon. So this is another paper we are working on now. And I already showed this slide. The idea here is we use this Gulf of Mexico model as a boundary condition to drive this 100-meter model, right? So we can also understand the dynamics in a small Barataria Bay area. And now this is the quiz, right? And what is answer here? So now let's look at what happens during Hurricane Laura and if my hypothesis was right or not right. So at that time, we have 3 hurricanes make landfall one after one. That is between end of August and early September. So on the top, this is the carbon dioxide record at the buoy. So you can see around here, right? This is where the penetration, the ocean shift from a carbon sink to a carbon source happens right at that point. So on the bottom, we see this is model simulated sea surface carbon dioxide, primary productivity. And this is the sea surface temperature. We try to look if there is any upwelling. So you can see upon the landfall of hurricane, at the beginning, we have a strong primary productivity, and the carbon dioxide is small on the sea surface. And here comes hurricane. It will push the plume further inshore, right? So in other words, is that the footprint of Mississippi River is largely reduced because of the squeeze of hurricane, right? So that will reduce the primary productivity in the sea surface, and that explains why carbon dioxide is not decreasing, instead it's increasing, right? Which proves that my hypothesis was wrong, because another evidence here is that this is a time series of sea surface carbon dioxide simulated by the model. We see the jump is right here in red color. Yeah, that is red color, right? And also at the same time, the salinity also jumped, which means the impact from the river decreased, right? And if we look into the chemical and biogeochemical, the primary productivity, we can see these 2 curves. This is the total alkalinity and the dissolved inorganic carbon. The blue line here is the ratio. And usually river water has a lower value. which means that the river's impact is decreasing. Right? At the same time, the gross primary productivity is also decreasing. Right? So all these different variables, we look at one point, we look at the spatial scale, all point that the correct answer should be which one? Should be C. Right? So that is the changes in Mississippi River plume dynamics. That's fine. NSF, we can talk to the funding manager. It's only $100K, right? It's not $1 million project, so that's okay. Hopefully. So, do we still have time or? In a minute, okay. Okay, I will go very quickly. So the last is, we have this 20-year hydrocast, right? So we can use this to train a machine learning model. I will just quickly show some results here. So for example, this is a paper we published. I will skip all the details here, but you can see this is observed hypoxia area, how big the hypoxia water is. And the red line, this is like predicted by the AI model. This is 1D area, right? And we are moving to the next stage. We have another paper that is under review. We try to forecast where can we find it. So we are moving from 1D to a 2D. So we use a deep lab plus a UNet, these two like AI model. And you can see AI can generate hypoxia distribution, not only the size, but also where we can find hypoxia. So this is, I will stop here. So the idea is I talk a lot about coastal hazard, right? And we have new hazards, so warming, saltwater intrusion, wildfires. And we can utilize this regional modeling system, try to enhance our capability of forecast and prediction, because in addition to this challenge, we also have a lot of opportunity, right? So we have blue carbon, we have offshore energy. So all this will also benefit from the forecast and prediction of ocean physics, biogeochemical conditions, flooding levels. Yeah, I will stop right here. Oh, I'm right. I was still here. So this is my group member, and they are doing all the heavy lifting. I'm just here to do the advertisement. So many thanks to different funding agencies, and also LSU provide a very generous support in terms of supercomputing. We are using, as Wan Hong mentioned, we are using more than 10 million. Now we are using more than 15 million each year. It's free at LSU. And the cost of supercomputer, if you know, is 10 cents per service unit, right? So the cost of the computation we are using now is worth about 1.5 million each year. And we get the support free. So that is a big appreciation to LSU HPC. Yeah, that's all. Thank you.
Yeah, thank you very much. It's a lot of work, coupling work. It's amazing. So any questions?
Questions, yeah. I know there's a lot of information. Yeah.
Question about the saltwater intrusion.
Right here.
I had a question about the saltwater intrusion into the Mississippi. Have you tried running your model to see what would happen if you took out dredging? Would you actually get the saltwater intrusion?
The dredging that is in the channel, right?
In the bird's foot.
Not yet.
We keep it really deep.
Yeah.
Yeah. So there's a competing force between the city of New Orleans and barge traffic.
Yeah. We don't have, that's a very good question, but we don't have the model. We are building a Louisiana model, now we have the model coverage, but this is for the Gulf domain, and it's not fully coupled. For the fully coupled in the Gulf area, so far, we only have the Galveston domain. That one I showed, right? And also the Florence, but that's for the East Coast. So what we are working now is we try to introduce this fully coupled high resolution model to cover the belt along the Gulf of Mexico. That's gonna be 100-meter horizontal resolution, but we are building one. And hopefully if we have that one, then we can perform some diagnostic, like to try to manipulate with like channel bathymetry and to see if there's any impact in terms of saltwater intrusion, how that will affect the dynamics in the channel.
Yeah, thank you for the excellent talk. So I have a related question, saltwater intrusion. So you have this two-way coupled model, right?
Uh-huh.
And you talk about how you couple the surface, I mean river
Uh-huh.
to the ocean, right?
Uh-huh.
But then I think there's also this subsurface runout. So I mean, I wonder how you guys define the interface between, you know, the shell. Maybe there's groundwater seepage and
Yeah.
stuff like that.
That's good. Yeah. The quick answer is not yet. Yeah. This is like, we don't have the capability to prescribe that yet. Yeah. I think the first step, but we know there's going to be a very important like contribution. Some like maybe 1/3 of the discharge, right, is from the underground water. Like we are working, I think we have a proposal that we are trying to working with some like a chemical oceanographer, try to use radon, and maybe we can simply prescribe some parameters to account for that, but we are far away from there yet. Yeah, this is gonna be the next 5 or 10 years work. Yeah, we are only, I think, 30% done. Yeah.
So any other question?
I had a question or really a challenge about your fully coupled model.
Mhm.
It's not really fully coupled because the boundary is static, right?
Yeah.
That should be an internal boundary that moves dynamically. You know, the ocean, where the ocean is depends on that competition, and where the end of the fluvial system is depends on competition between them. And by fixing it, aren't you over constraining your model?
By fixing is we only fixing where they talked.
Yeah, but by fixing where they talk.
If they are river or ocean is determined by the model. So in other words, it's no longer a river model or a ocean model. And we just like use different equations. So we have hydrological equation, we have ocean equation, and on the boundary is a reduced physics, right? So it's a fixed talking boundary, but not necessarily the boundary we call it ocean or like river or land, because there's no boundary. Yeah, for example, like you can see that the salt water, they can get into the beach area. And in that case, the WRF-Hydro is acting like an ocean model because it can also handle like the salinity. Yeah, so the fixed boundary is really, we fixed where they're gonna talk. So that is good because like we don't have to spend a lot of time trying to determine if this is ocean or land. We just determine where they want to talk, and they can negotiate by themselves. And we can tell that should be ocean or river. Yeah, it's a blurred boundary.
Any other question? Chat is pretty, yeah, pretty quiet.
I'm pretty quiet, okay. Yeah.
I have a question.
Question?
Yeah.
Bridget, you have?
Well, I think we'll be talking to you in a minute, so.
Okay.
I'm gonna- we have lots of questions.
Yeah, no problem. Yeah, no problem.
Okay, we can close the seminar today. Thank you. Thank you very much, George.
No problem. Yeah. Again, we have stickers in the back. If you take one, yeah, just scan it. It will bring you to the web page. Thank you all. Thank you everybody on the chat.